Okay guys, so now we're going to do chemical properties or nucleophilic substitution reactions, okay? This one we're going to focus on. Now we have spent a lot of time talking about the mechanisms of nucleophilic substitution reactions, SN1 and SN2. We talked about when they're favorable, when they're not, the stereochemistry, we talked about all that. We have also talked about what is a nucleophile, what is the strength of a nucleophile, why only stronger can replace weaker. We talked about the solvents which determine the strength of a nucleophile. We talked about all that also. But what we have not talked about are the reactions themselves, okay? So we're going to do that now. So this comes under chemical properties. Okay, so basically the characteristic reactions of haloalkanes. Okay, and the important thing we need to remember is that the characteristic reactions of haloalkanes are haloalkanes are very useful. Okay, so you can prepare a lot of things from a haloalkane because of the flexibility of that bond. Okay, so we're going to see that. So in the following cases, we are going to do nucleophilic substitution on the halide which is attached to our group. The halide is considered to be either a chlorine, bromine, or an iodine, of which iodine is most generally preferred because iodine is the fattest, right? If you are bigger, you're going to have more electron through repulsion, your bond is going to be longer, your bond is going to be weaker. So it's easier to kick out an iodine than to kick out a chlorine, right? See, no matter what mechanism pathway it goes through, right? No matter what type of an R group this is, you want this bond to break at the end of the day, right? Somehow. So to have the weaker bond to start with is just a better starting place for us, right? So generally we take an iodide to show these reactions. First step. Now I'm going to just start talking about the possible reactions which RX can undergo. So it's going to be a pretty filled board this time, okay? So first reaction, KOH, aqueous. Who's a nucleophile? KOH in water gives me OH minus, right? So OH minus is a nucleophile. What does he want to do? Attack, X minus goes away, there's a K plus in solution. So you get KX plus ROH. Okay, so that's the first one. Why can we not use alcohol in KOH? The reason is because it will cause dehydrohalonation and create an alkene instead. Okay, next one. Aqueous KCl. Okay, the nucleophile is Cn minus. Same procedure. This attacks, this leaves K plus in solution. I'm going to get KCn plus, RCn plus KX. Okay, that's my second step. Third one, we'll do AgCn this time. Aqueous. Who is our nucleophile? And the answer is it is Nc minus. What's the difference between Cn minus and Nc minus? Well, they're isomers of each other, right? But the negative charge is the bonding site in this case is on the carbon atom, while the bonding site in this case is in the nitrogen atom. Okay, so we'll discuss that right now in about 1 minute. Anyways, since Nc is the is the nucleophile, it's going to attack. X minus is going to leave as an Ag in solution. You got AgX plus RNC. Okay, so that's your next product. And then there are many more. So you can take KNO2 aqueous. Your nucleophile is going to be ONO minus. Okay, that basically means it's the nitrite ion. Right? You get RONO plus. You will also get a KX. Right? Keep it coming. So the another reaction could be AgNO2. Once again, this potassium and Ag, okay, they do a lot of things similarly, but then they're actually not similar. For example, KC and AgCN, there's a difference. Similarly, KNO2, AgNO2, there's a difference. The nucleophile here is NO2 minus. Okay, so the product will be NO2 plus AgX. Okay, so that's pretty much it actually. These are all your possible nucleophilic reactions. Okay, you still have more. You can react this with KSH instead. So KSH, which is basically a thiol instead of an alcohol. So you get RSH plus KX. So that's also possible. Everything else is not going to be any big deal. So if you understand, basically all you need to understand for this is nucleophilic substitution reactions, right? So if any compound I give you, you can just find the anion there, the nucleophile there, and do it yourself and find out. The interesting thing, however, is the question as to why KCN and AgCN give me different products, and why do KNO2 and AgNO2 give me different products. That needs a little bit more clarification. So that's what we're going to do now. So for that we need to see isomers are basically what? Same formula but different structure, right? So we got to draw the structure to figure out. First of all, KCN is an ionic compound, okay? So the only this is basically going to be my nucleophile. Can you see the negative charge is localized on the carbon atom? On the other hand, AgCN is covalent, okay? So if I draw the structure, it looks something like this, with something like a lone pair here, okay? Now we assume that this carbon is like inorganic carbon because remember the first point is carbon's electronic configuration is 1s2, 2s2, 2p2, right? It's the sixth element in the periodic table. What we're going to do now is we generally said in organic chemistry s electron is excited with p orbital, right? So your electronic configuration becomes 1s2, 2s1, 2p3, right? And you have 4 unpaired electrons, that means 4 bonds possible, right? That is basically the point. The case however here is that you can just assume this to be an inorganic carbon because it's satisfied with 2 bonds alone, okay? Am I missing something? The answer is okay. So basically what will happen now is when this guy dissociates, although it's covalent, right? Nitrogen is going to have a negative charge on top of him, okay? And the reason for that is because I am going to have to erase this for now. I am just showing you the nucleophile for now. Just give me a second. See, this is how it's going to work, okay? This is if I had just the isocyanide. This is the isocyanide ion, okay? But in AgCN, this is how it works. It's covalently bonded, right? Nitrogen has a lone pair here, okay? So nitrogen will strike whenever it needs to. So this lone pair actually acts as a donation site. In this case, the negative charge acts as a donation site. Also, you guys know, through all these cases, you guys got to remember the fundamentals which we learned, which is that a stronger nucleophile can only replace a weaker nucleophile, right? Not the other way around. So you can see why CN does the job because carbon nucleophiles are highly strong compared to your other nucleophiles, right? Remember we wrote CH3 minus, much stronger than NH2 minus, much stronger than OH minus, much stronger than F minus. Generally, carbon nucleophiles are much stronger than nitrogen, much stronger than oxygen, much stronger than fluorine nucleophiles. Okay, so that's another thing you want to keep in mind. Don't always try to think about the basic stuff again to make sure that everything is making sense. Okay, so this lone pair is just like it's not going to participate much in bonding. Nitrogen's lone pair is what participates in bonding. Okay, and this is a case which we call CN minus is what we call an ambident nucleophile. Ambident nucleophile. Ambidextrous means you can use both your hands, right? Ambident means you have more than one bonding site. So both the carbon and the nitrogen can act as bonding sites depending on what type of a compound they are in. Okay? So that's the argument. Similarly, you can work it out for AgNO2 and KNO2. Okay? So let's try to work it out for AgNO2 and KNO2. So what happens is you got potassium K plus and you got NO2 minus, right? And you saw that it gives me ONO minus, right? So it's going to be O minus, single bond and double bond. This is the ion, right? You guys should be knowing how to draw these structures. You learned this in 11th grade, right? Chemical bonding class. So this is basically KNO2. This is my nucleophile here. Oxygen is the bonding site, right? Then I can have AgNO2, right? Now in AgNO2 what happens? You get, let me first draw so this is basically called nitrate, right? The other structure can be this. Okay, so N double bond O, single bond O, minus, plus, minus. This is a highly unstable structure. It's not actually real, all that stuff. But what you want to keep in mind is that I can always, so you can always argue why the nitrogen is the bonding site here. Okay, so that's the first thing. The second thing is that this is a covalent structure, right? So this is basically the ion, and in the covalent structure it will look like this. Okay, and you all know that here. You will ask me, well, Hari, then why is the negative charge not attacking the lone pair bonding site? The answer is that, see, this double bond and this negative charge are in resonance. Okay, so it's not as much available as this lone pair. Lone pair is not going anywhere, right? So everybody's good. So that's why this is happening. Okay, so you might want to brush up on the structures. If I've done a mistake in the structure, please let me know. But as far as I can see, this seems about a little decent. Okay, so that's the second case. So this is also an example of an ambident nucleophile. So in your test papers, people like to ask you, how will you prepare potassium isocyanate, 2-methyl propane isocyanate or something like that, right? So basically you will have to remember that you are using different reagents for different purposes, although they might seemingly have the same molecular formula. Okay, so that's one thing you need to know. The second thing I want you to know is that we do not have the same discussion for haloarenes. And there is a reason why we do not have the same discussion for haloarenes. And the reason is that haloarenes have this interesting property. For example, you know how resonance works and stuff, right? So if I have, say, chlorobenzene, let's take chlorobenzene, why not? So let's take chlorobenzene, let's take chlorine. And you guys know that chlorine has a lone pair, right? Chlorine obviously has a lone pair. And it actually has 3 lone pairs. And this gave, so 8, right? So everybody's happy. Now, if you notice very carefully that this lone pair and this double bond are in conjugation. So what can happen? This can come here and this can jump here, right? So that's my first resonance this thing. So Cl plus with 2 lone pairs. This is double bond, and we can draw. This is a negative charge. So this is one of our resonance states. You can keep going now. This double bond shifts here. This negative charge comes here. So the next resonance state will look like what? Negative charge, double bond, double bond, double bond here with the positive charge. Then what can happen? This can shift. Oops, sorry about that. You can get one negative charge. You get a bond here, double bond, here plus. And then this can finally shift and you get the same thing all over again, right? So if you see, 3 out of 4 major resonance frequency, 3 out of 4 major resonance states have a double bond between the carbon and the chlorine. 75% of the time, this is true. Actually, not exactly 100%, because an uncharged system is more favorable and more contributing as a charged structure. But I'm pretty sure you can say more than 50% of the time, there's a double bond between carbon and chlorine. So you say that the carbon halogen bond possesses a partial double bond character. Okay, it's not a single bond anymore. It's not all that nice stuff where it rotates about the internuclear axis, it's symmetric, blah blah blah. It's not anymore, because most of the times it has a double bond character. The implication of the fact that it has a double bond character is that the bond strength increases. Strength increases, effective bond length decreases, because of which it becomes supremely hard for any other nucleophile to come and kick this guy out, because it's a double bond, not a single bond anymore. Life isn't that easy. You cannot break that double bond very easily. Have you ever heard of a substitution reaction where a double bond is broken? It's impossible, right? It's literally impossible. You cannot have one nucleophile attacking and making 2 bonds. So we say nucleophilic substitution reactions do not generally happen in haloarenes. So haloarenes are resistant to substitution using nucleophilic substitution reactions. Okay, so that's another fact you got to know. Please, in the exam, if you are asked this question, remember to write the words partial double bond character. Okay, So please remember to write those words because you know how crazy they are about keywords, right? So you want to keep that in mind. I think that's about it. So I will see you in the next video with a short note on Dow's process, and then we will move into a little bit more nicer, a little quick discussion about physical properties like melting point, boiling point, all that stuff, and then we will jump into tests and we will move forward. So solubility, all this good stuff you'll see soon. So take care guys, see you in the next one.